Hey, what's up guys, Yankee here, and in this video, we are going to be building a large language model application which will be able to search the web for the most relevant results so that you are not just limited to the knowledge of the large language model. So let's see the flow of our application. When the user comes to our application, they are going to put the query and then the application is going to perform an internet search and then it's going to return a bunch of URLs. Since we will be doing this ethically, we are going to check robots.txt so that we identify which URLs can be scraped and which we cannot scrape. And based on that, we will pass the valid URLs to our web crawler. And then it's going to generate markdown, all the contents of the page that we crawl. We are going to chunk it. And then we are going to save it to vector database, and whatever query that user put on our application, we are going to search the vector database against that query, and whatever result is provided, we are going to pass it to the large language model and it's going to generate a response back to the user. So let's see a demo of this application. So this is what our application is going to look like. We have the title of the application, LLM web search. We have an area to put our prompt query. And then we have this toggle if we want to perform a web search or if we want to put the query directly into the large language model. So for this demo, let's see what is the darkest material available. And this query will directly go to the large language model and generate an answer. As you can see, it's pretty quick. Now, if I want to enable web search, I'm going to enable it and let me search some real-time information. Maybe who won the Grammys for best rap album in 2025. So I'm going to search for this result. It's going to scrape the websites and it's going to give me the answer. And here comes the answer. I don't know how to pronounce the name of the artist, but C was the one who won the Grammys for the best rap album for a mixtape, Alligator Bites Never Heal. And you have these other facts that the LLM thinks is relevant based on the context we provided to the large language model. So let's get started in building this application. So I am in my code editor. I have a project directory called LLM app with web search. I have created and instantiated my virtual environment and I have a single file called app.py. So first of all, let's start by installing all of our application dependencies. And this is a long list. We have Streamlit for our UI. We are using crawl for AI. To crawl the website, we have unstructured markdown, which is required by LangChain community when we later on load the markdown documents. We are going to perform web search using DuckDuckGo. So we need DuckDuckGo search. For vector database, we are going to use ChromaDB, LangChain community for its utils, and Ollama as our method for calling the large language models. So let's install all of them. Now that this is installed, we are also going to install Playwright and install because crawl for AI uses Playwright under the hood. So we are going to need the headless browsers for this to work. So we are going to do Playwright install. I've already installed the necessary browser packages, so this is just going to stay like this. Now let's jump to our code. First of all, let's bring in some imports for our front end. And for this, we are going to use Streamlit. And I'm also using async.io package because we are going to use crawl for AI, and asynchronously, we are going to crawl a lot of different pages. So we need async.io. So we have this function async def run. So this is going to be the entry point to our application. And then we have this Streamlit set page config where we are putting the page title as LLM with web search. So whenever you open a browser tab, the page title is going to be LLM with web search. And then we are going to put a header, which is going to be called LLM web search again with this search icon. And then we are going to put a text area where the placeholder will say add your query. This is where the user are going to add their queries. We also put a label, but we are going to hide it for now. And then we are going to put a toggle. Is it a web search or is it not? If it's a web search, we are going to pass the query to the crawler and we are going to crawl and do all the things that we showed earlier. If not, we are just going to pass the query that the user puts here or the prompt directly to the LLM and we are going to generate the result from the LLM. So is web search is going to be a toggle. The name is going to be enable web search. The default value is going to be false and key is going to be enable web search. So if you are using Streamlit session instead of this variable, then this will come in handy, but we'll talk about this in a later video. And go is going to be a button. So whenever you press go, we are going to start our application given that the prompt is there. Once we have that, let's add our main block. If name equals to main, then we are going to do async io.run. We are going to create an event loop, and then we are going to run this function asynchronously. With that in place, let's see our application, how it looks. So I'm going to do streamlit run app.py. The application will be running on localhost 8501. And as you can see, there is an error. So I'm going to update here. It's going to be hidden. And then if I go and refresh, it's gone. So as you can see, the UI of our application is ready and functional. So let's go back to our editor, and then we need a new import, and it's going to be from DuckDuckGo search. We are going to import ddgs class. And with this import in place, we are going to create a new function, which is going to be called getWebURLs, and it's going to take a parameter called search_term. So this is basically going to be whatever prompt that the user puts in our application, and then the number of results is going to be 10. It basically means how many web pages do we want to get back after we perform a web search, and the return is going to be a list of string. So we have put all of this into a try catch method, and now let's go and see what we are doing line by line. So there is this variable called discard URLs. So whenever I am performing a web search, I do not want any results that contains youtube.com, britannica.com or vimeo.com, because I cannot really scrape the results out of it based on my test earlier. So you can add more URLs here based on your use case. I'm going through each of these URLs and I'm modifying their search term, which is the prompt, and I'm adding -site and then the URLs. This is basically a special character which allows me to discard all of these URLs. So if I want to see what my final search result looks like, all I have to do is do st.write, and then I can do search term so that you can see exactly what it looks like. And if we come down, we are finally initializing the class ddgs, and then we are going to do a text search with the search term, and the max result is going to be 10. And then when we get the results, we are overwriting the results variable here. So when we get the results, we are going to take the href value from the result, so just the URL. We can also do st.write and do results to see what kind of output it provides to us. And after that, we are just returning results. And while doing this, if there is any exception, we are just going to say fail to fetch results from the web, and we are going to display the result as it is in its string format. We are also going to print that result on our terminal, and we are going to write it on our front end as well. And basically we'll call the Streamlit application to stop. So sometimes you can get too many requests when you are using DDGS search. So make sure you're not performing a lot of web searches within a same minute. You can also swap this for something else. This function is pretty generic. And in my run section, what I can do is that I can put this here if there is a prompt, and if the user presses the button go, and if the user toggles is web search, what I'm going to do is I'm going to get web URLs. I'm going to pass the search term as my prompt. If there is no web URLs, I'm just going to show it on the front end like no results found, and I'm going to stop the application. For now, there is no else condition, so we always assume that we are going to make a web search. So let's go back to our application and enable web search. Then I'm going to just write, can you see John Cena, and I'm going to press go. So as you can see, this is the query that we are passing to DuckDuckGo. So can you see John Cena -site youtube.com, -site britannica.com, -site vimeo.com. So we do not want any results from this website. And once we have the results back from st.write results, we are going to get this. So there are many objects. So the first object contains title. So John Cena is hilarious, you can't see me, meme, explain, whatever. So there is this href that we are collecting for each of the results, and there is a body as well. This is the description from the website itself, not the body but the description. And yeah, that's kind of it. And if you minimize this, we just have a collection of all of the URLs from the websites. So we said we want 10 websites starting from 0th index. We have 9. We are going to crawl through each of them, but before that we need to make sure that we are crawling it ethically. So we are going to check the robots.txt file for each of these websites. So let's say you have screenrant.com. So if I take this URL and go to robots.txt, so there are going to be some some disallow rule which basically says that do not go into these paths and try to crawl anything like that. But if there is nothing, then you can crawl it. So we are going to respect that, and we are just going to crawl the pages that a website allows us to crawl. So let's go back to our code, and then we are going to add a new function here which allows us to perform ethical web crawling. We don't have URL parse, so what I'm going to do is import it. So from URL lib.parse, import URL parse, and then we don't have robot file parser imported yet. I'm going to import it. So from URL lib, robot parser, robot file parser. So this is a built-in class from the Python library itself. So let's see how this function is working. We are taking a bunch of URLs, and then we are going through each of those URLs, and we are trying to find the robots.txt. So our URLs, if you go to the front end, comes like this. So from this URL, we want the scheme, which is going to be HTTPS, and it's going to have the netlock, which is going to be up to screenrant.com, and then followed by slash and robots.txt. Inside of the robots file parser, we are going to pass the URL from where it's going to open that web page and get its content, going to read it, and it has a very handy function called can fetch. So if we pass the URL, right, this whole URL that we get, and we check if we can fetch it or not, then it says like true or false. So if we can fetch it, we are going to push that URL into allowed URLs list. If not, we are just going to continue through our loop, and we are going to check other URLs. If there is an exception, meaning if there is no robots.txt file thing, we basically assume that we are allowed to scrape that website. So we just put that URL into allowed URLs list, and we return the allowed URLs. If we come down here, let me delete these debug statements. And instead of returning the results, what we are going to do is return, and the name of the function is check robots.txt, and we are going to pass the results, which is going to be a bunch of URLs. And now once we have all of these URLs that we can scrape, now we need a crawler that goes through each of these web pages and takes out the content. So for that, we are going to be using crawl for AI. We are going to need a bunch of imports. So yeah, we are going to use async web crawler. We are going to configure the browser. We are going to bypass the cache. So we have this cache mode. We are also going to do a crawler run configuration. And yeah, we are going to perform BM25 content filtration. And since we will be converting the contents of the web page into Markdown, we are going to have a default Markdown generator. And for type hinting, we are importing crawl result. So let's bring in our function to perform the web crawling. So for this, I'm going to create a function, and this is going to be an asynchronous function, and it's going to be called crawl web page. I should actually say crawl web pages because it's going to crawl multiple web pages. So it's going to get a list of URLs as a parameter, and it's also going to get the prompt that the user has typed, and the return result is going to be the crawl result. Here we are using BM25 content filters. So whenever we are crawling the website, we are going to use this BM25 or the best match 25 content filtration strategy. So it's kind of like vector search where, you know, whatever prompt the user has passed, the crawl for AI will try to get only the matching content from the website. So this is another bonus or benefit that we get, so that we get the most accurate result. The next one, we are defining a variable called MD generator or the Markdown generator. And we are using default Markdown generator from the crawl for AI itself. And the content filter is going to be BM25 filter. So it crawls the website, and then it tries to generate a Markdown from that crawled result, and it's going to apply this filter to the contents of the website, and it gives us the final Markdown, which is also called fit Markdown in this case. And if we come down, there is this crawler run configuration. So whenever the crawler is running, it's going to generate the Markdown. So Markdown generator is going to be this class. So you can use other classes as well. You can check the documentation for crawl for AI. The next argument here is excluded tags for crawler run config. So we are going to exclude tags like navigation, footer, header, form, image, hyperlinks, and things like that. And then there is only text equals to true. So basically, whenever we are crawling the website, it just tries to get the text Else by default, crawl for AI also fetches images, tables, and all these other stuff. On the next line, we are excluding any social media links that it finds. So keep data attributes is false. It basically does not return any data attributes. Cache mode dot bypass. This basically means that whenever we are running the crawler, we do not want to use the cache that it creates. So every time it's going to be a fresh crawling operation. And the next one is remove overlay elements. So whenever you have pop-ups or anything like that on the website, it removes those overlay elements and tries to fetch the main content. I'm also passing a user agent, so this might not be necessary, but in my case, I have just added it. So you can generate a user agent using a large language model. And the page timeout, so whenever it tries to crawl the page, it times out within 20 seconds. The data we need to put here is in milliseconds, so it's 20,000. And when we come down, there is a browser configuration. So there is a crawler run configuration. So when the crawler is crawling the website, and then there is browser configuration. When the crawler wants to crawl a web page, it needs to open a headless browser, and this is the configuration for the browser. And once it opens the web page and tries to crawl the result, this is the configuration for that crawler. So let's come down to browser config. Headless is true. This is by default. Text mode is true. So it just tries to load the web page with just text only. And then light mode equals to true. It basically tries to strip away any of the extra things that comes with the web page. So if we look into browser config and look for light mode, disables certain background features for performance gains. And if we look into text mode, it basically says that disables image and other rich content for potentially faster load times. So this is what we want. We are just interested in the text content, so we do not want anything else. And now if we come down, we have this context manager, which is called async web crawler. And then the configuration it's going to have is the browser configuration. We are going to use async with, and then the name of this crawler or this context manager is going to be called crawler. And results is going to be, we are going to await on the results of crawler.a run many. So this is basically a method provided by crawl for AI, which allows us to asynchronously run multiple URLs. And whenever we are crawling, we are going to use the crawler configuration. So whenever we are running this method, it tries to crawl most of the websites at once. It also keeps in mind how much memory is being used on the computer and everything. So it's pretty handy. You know, it does a lot of things behind the scenes, like trying to reconnect to a website and things like that. Basically, once it's done crawling all of these websites, all of the data will be stored on the results variable, and we are returning the results variable. So now once we have the data, we need to put that data inside of the vector database. So for that, we are going to set up vector database now. If we come to the imports and then paste, we are going to need ChromaDB. We are going to need temporary file. Because whatever markdown is being generated by crawl for AI, we are going to save it in a temporary file and then load it. Then we are going to have some configuration for ChromaDB. So we have this settings class, and for embedding, we are going to be using Olama. So we are importing the ChromaDB's internal class, which is called Olama embedding function. And we are also going to need LangChain community document loader. It's going to be unstructured markdown loader. And for text splitting, we are going to use the handy recursive character text splitter. With that in place, let's create our another function, and it's going to be called get vector collection. This function basically takes nothing and it returns ChromaDB collection and a ChromaDB client. We are going to create a variable which is going to be called Olama EF for embedding function. And we are going to use the embedding function that we imported earlier from ChromaDB. We are going to pass the URL for our Olama server, and then the model is going to be nomic embed. This is my go-to model for embedding text because it has a large context window and it has high dimensions, which is pretty good for vector databases. But before you run this, make sure you have Olama running on your machine. So we are creating a Chroma client, and in this case, this is going to be a persistent client, and it's going to have a path of ./web search LLMDB. So basically, we are going to persist our vector database on our disk, and this is going to be the path. And the setting is we do not want to send any anonymized telemetry. So anonymized telemetry equals to false. We are going to return a collection. So Chroma client, we have this client connecting to this database, and we are going to perform get or create collection. And the name of the collection is going to be web LLM. The embedding function is going to be Olama EF, which is going to use nomic embed. And the metadata is going to be cosine. So it's going to use cosine function or the cosine distance whenever we perform vector search. And again, we are going to return a chroma client. So this is going to be a tuple of collection where we want to perform some things on the collection like inserting, querying, and we want to get the chroma client so that it's handy to perform other operations like deletion later on. The next thing we need to do is we need to get this connection and add our documents to the vector database. So let's create another function. So this is going to be a bit chunky, but bear with me. So this is going to be called add to vector database, and it's going to have results, which is going to be list of crawled result. So whenever the crawling is complete, we are going to pass all of that crawling data into this function. So the first line in this function is it gets the vector collection, and it just needs the collection, which is going to be web LLM, and then it's going to loop through all of the crawl result. We also have this placeholder list, which are documents, metadatas, and IDs, which is required to store inside of the vector database. For text splitting, we are going to use recursive character text splitter. The chunk size is going to be 400, and then the chunk overlap is going to be 100, and the separator is going to be a paragraph break, a line break, a full stop, question mark, exclamation sign, space, and so on. So whenever we get a big chunk of text, we are trying to split it based on these delimiters, and the size should be around this, and the overlap between the first chunk, second chunk, third chunk is going to be this. And now if result.markdown v2, the result is an instance of crawl result which comes from crawl for AI, and we are trying to see if there is markdown v2. Since we have configured our crawler to give us markdown result and we are using BM25 content filtration, the result will be stored in markdown v2. You can also do markdown, but this does not use the BM25 filtration, so for that we need v2. This is set to change in the later versions of crawl for AI, but for now it's not that important, but just keep that in mind. And if we have result.markdown, what we are going to do is result.markdown v2 and get the fit markdown. Fit markdown meaning we have applied the BM25 content filtration strategy, and the output is the fit markdown that is fit for our use case. And if there is no result.markdown v2, we are just going to continue, meaning we are going to continue with the loop. Apart from markdown v2, we also have HTML if you want to perform anything with the HTML. But yeah, in our case, it's going to be markdown v2. So from the crawl result, we have the markdown content, and then we are going to add that content to a temporary file. So we are going to create a named temporary file. We are going to write to it. The suffix is going to be .md for markdown, and we are not going to delete it yet. And then from that temp file instance, we are going to write the markdown result, which is the fit markdown. And we are going to use temp file.flush so that nothing remains in the buffer. Everything is pushed to the temp file. And now we are using the loader from which we are going to load the recently created temporary file. So unstructured markdown loader from LangChain allows us to put the temporary file. So when you do temp file.name, it gives us the path to that temporary file, and the mode is going to be single. I think there is single, and let's see. Yeah, the mode is single, multi, or all, but the default is single, but I'm passing it explicitly here as well. And then on the next line, we are loading the document. So loaders.load docs. This gives us a document format from LangChain, which we can put on our text splitter. So text splitter is recursive character text splitter. We got our markdown. We converted that markdown into a temporary file. We loaded that temporary file into a LangChain format called document. And now we are taking that document and splitting it based on these parameters. So for that, we are going to name a variable called all splits, and using text splitter dot split documents, we are going to pass all the docs and it's going to split it. And now we are going to normalize the URL, and it requires a function called normalize URL, and the result is again a crawler result, and the URL is basically the name of the web page where the result is coming from. We don't have the normalize URL function yet, so we are going to create it. Let's come up. We are going to put it here. So normalize URL, basically it gets a URL. It's going to replace https:// into empty string. It's going to replace www. into an empty string, and if there is a / dash or a dot, it's going to convert it into underscore. And we are also going to print the normalized URL. This is to provide the ID to the vector database. So let's come down. We have the normalize URL function now. And if we have all the splits, we are going to loop through all of these splits. And we are also going to enumerate, meaning we can get the ID for each of the split. We have these variables, empty lists for documents, metadatas, and IDs. So documents is going to be the splitted markdown. Metadata is going to be basically the name of the URL where this data is coming from and things like that. And the ID is again going to be the URL in a normalized form. So if we come down, as you can see, document.append split.page content. So whenever we are splitting all of these documents, we have this page content which we can access. For metadata, we are passing it as a dictionary where the source is result.url, and then the ID is going to be the normalized URL followed by the ID, which is going to be 0, 1, 2, whatever, right? And then we are going to obsert all of this data, so documents, metadatas, and ID into our vector collection. So if we see vector collection, this is going to be our web LLM. So we can also do st.write all splits just to see what kind of data we are dealing with. We can also do st.write result so that we can see what kind of result we are getting. Till now, we can perform web search, get all of the URL, pass it to a crawler, crawl the web page, get the markdown content, and then store it to the vector database. So if I come down, I'm going to add this collection chroma client equals to get vector collection because I want to perform some actions here as well with the vector collection. If we have the web URLs, what we are going to do is we are going to crawl the web page. In our case, web pages, because we renamed it earlier. We get a bunch of URLs and then we are passing all of those URLs inside of our crawler. And we are also passing the prompt for BM25 filter. And whenever we get the result, we are adding it to the vector database. Let's make sure we have our server running. Let's go to our browser. This was the result from previous search, but I'm going to do it again because we have removed all of these debugging lines. So we are going to see a crawler result, right? So crawl web page and then add to vector database. So we have st.write what kind of result we get from crawling and then what kind of result after making splits. So let's see that. So this is the result object we get from crawling the website. So this one is st.write result, each individual result. And as you can see, we are trying to take result.markdown v2.fit markdown. I'll not be able to show all of that here because there is a lot of data. But what we did was take result.url. So if I do URL, yeah, it's on the first line. So we are taking this as our metadata. And we are normalizing this as well. So we are taking this as our metadata and we are normalizing it as well. I think I should put st.write normalized URL as well. That's for later on. So if I minimize this, yeah, and these are all the splits. So we also created splits. And as you can see, we have metadata source is still the temporary file directory. But as you can see, the page content is going to be the splits from the markdown that our web crawler crawled from. And that's what we are accessing here. So split.page content, it's going to be this. So there is going to be a lot of these. Okay, we have seen this. All we want to see is what does a normalized URL look like. But after this crawling, I think if we go here, we have our web search LLMDB, which is our vector database. If we go to chroma.sqlite3 and if we look into the embeddings table, we can see that the embedding ID is going to be the normalized URL. So it's basically distractify.com/p/y is zone Cena invisible /0. So it's normalized like this with all the underscores. So that is what the normalized URL looks like. So I'm just going to remove that debug statement. We do not need it. So let's see where we are till now. We have the crawler, we are adding it to the vector database. Now, the next thing we need to do is we need to query the vector database and get the result as a context to pass to our LLM. So for that, I'm going to add this line. Q results represent the query result from the collection we defined earlier. We are going to do collection.query and we are going to pass the prompt as a list, and the number of results that we are going to get back from the vector database is going to be 10. And from that result, we are just going to grab the first one. So let's do st.write q results. Before that, I also want to write st.write query results so that we know what we are dealing with. And the context is basically going to be query results.get documents with the index of 0. We are going to see in a second what this data structure looks like. And after we have got the context text, we are not going to need the web search result after we get the context. So we are basically going to delete the collection called web LLM. So whenever we are performing web search, each query is going to be unique. That's what we are going to assume for this application. So user might search for a lot of things on the website. There is absolutely no need for us to store it on the vector database. So we can perform vector search, get the relevant text from the vector database, and just delete the collection. That's what we are doing here. Let's see what our context looks like as well. So st.write context. I'm going to copy this and I'm going to rename it as context. So let's see what kind of data we get. I'm going to enable web search and search again. So this time we are going to see what query results we get from the vector database and what kind of context we get out of the query results. So from query results, we are going to get 10 documents from 0 to 9. So these are the IDs of the document that we have fetched. So I'm going to minimize this, and these are the documents. So this is how the data is stored on the vector database, right? So metadatas, all of this source that we put earlier, and these are the documents or the real text that we want to grab. Let's minimize this and let's get the context. So this is all the context that we are fetching. So we are passing all of this text into our LLM and we are trying to get the LLM to give us an answer or a result based on the text that we have. So all of this text came from all of these sites, and based on our search query, these are the most relevant text that we can show to the user. So let's go back. Let's delete our debug statements. We need to create a function that calls a large language model and gives us the result. So for that, we are going to use ollama. So let's go to the very top. We are going to import ollama and then come down. And then we are going to create a function that is going to be called call large language model. We don't have a system prompt yet. I'm going to add it later on. So call LLM function basically takes a parameter called prompt, whatever user has typed with context. This basically means that have we enabled web search on our UI or not. So with context means web search enabled. If this is false, then it basically just tries to pass the prompt to the large language model. We'll see that. So context is going to be the context or it's going to be none. So if this is without context, the context is going to be none and we have the default value of none. We are preparing a payload or the chat history for the large language model. It's going to be called messages, a list, and then there are roles. So the first role is system, where we pass the system prompt if this is with context. And then the second one is the role of a user, where we are asking the question and we are passing context and question. So let's bring in the system prompt. So this is our system prompt. So if you have watched the video of RAG with large language model, the system prompt is exactly the same. So we are trying to ground our large language model with these instructions. So what we are saying is that it should provide answer based on the context we provide and nothing else. So we will provide the context and the question. And we are also trying to give it a bunch of instruction on how to answer the question, how to format it. So you can find this link in the description below on the code base. So I'm just going to minimize this for a minute. And if we come down, if not with context, this basically means that if we are not performing web search, what we are going to do is that message.pop 0. So it's going to remove this from the messages array and then only this will be left, right? So this will be the 0th index item. So what we are doing is messages get the 0th index item, and for the content, we are just overriding all of this with just the prompt. So just the question from the user, we will be passing to the large language model. If this is with context, so all of this will be used as it is, no change. And for the response, we are using ollama.chat method. And for the model, we are using llama 3.2 3 billion parameter. So if you do not have this model, all you have to do is ollama pull and the name of the model, and this will be pulled on your system. But you can use any model of your choice. In my testing, llama 3.2 3 billion performs amazing. Stream equals to true. We want to stream the results as they come, and the message is going to be this messages or this one. Since we are going to stream the messages, we are going to get this in chunk. So we are getting each chunk in the response. So once the LLM is done producing the result, it will pass the done as true. So it is checking if the chunk done is false, meaning it's not done yet. We are yielding the results. So this is basically a generator function. So it's going to yield each chunk one at a time. So chunk also has, like, apart from done, it also has message and content, which contains the real text that we want to show to the user. And if the chunk done is true, then we are just going to break out of this function or this loop. So once this is done, we have most of the logic of our application ready. So let's go to the very bottom. We have the context and everything here. So let's come down here. So basically, after getting the context, what we are doing is we are calling the LLM. We are passing the context to it. We are passing the prompt to it. And with context is basically is web search. So if we toggle is web search as true, then it's going to be true. If it's turned off, it's going to be false. And once we get the result from the LLM, we are going to stream it to our UI using st.writeStream, the LLM response. And else basically means that if the web search is disabled, it's basically going to take this prompt, pass it to the large language model, and generate the response from it. So let's try to do this. Since we have disabled the web search, this is directly going to go to the large language model and it's going to generate an answer. Like, I'm a large language model, I do not have the ability to see or whatever, right? But if you want to do generic tasks like write a poem about LLMs in 5 sentences, it's going to go directly to the large language models and it's going to, generate the answer. So if we enable web search again, now we can search for real-time results. So I'm going to search who won Nepal Premier League, NPL cricket. So I'm going to perform web search. And if we come to our terminal, we can see all of the web search results here as well. So it has initiated the crawler and it's going to crawl all of these websites in parallel, like you can see. And after it has started crawling the websites, it's going to convert it into Markdown. It's going to pass it to the vector database. It's going to query it and we are going to get the result. So as you can see, even if it gets an error, it can recover from it. And normalize URL, we can see all of these and we have offsetted it into the collection. And now, it has basically generated the result. The winner of Nepal Premier League cricket is Janakpur Bulls. Yep, that's true. And now let's try a new query. So what is new in iOS 18.3? So it is getting the results from the web and it is writing the answer based on that web result. So that's it for this video. Hope you enjoyed this video building a large language model application which can perform web search and get real-time data from the internet. If you like this video, give me a thumbs up. If you want to see such content in the future, subscribe to my channel. I'm Yankee and I'll see you in the next one.